Hello and welcome to Sigma Phi's Google Hangouts with our distinguished lecturers. I'm Katie Burke, Digital Features Editor at American Scientist Magazine. This particular Hangout with Dr. Mark Serreze from the University of Colorado Boulder is sponsored by the Sigma Phi chapter of the University of Arkansas Fayetteville and the American Meteorological Society. So hello to the members of that chapter, as well as other Sigma Phi members or followers on social media who are joining us. For those who are new to this talk format, you can ask us questions at any time during this question and answer session. And if you're a Sigma Phi member, you can also submit follow-up questions after the talk by going to the Sigma Phi Communities page, the lab, and then we'll send those questions on to Dr. Suresh. But for those who are joining us on Hangouts, you can use the Q&A format on the right side of your screen to submit questions. So today we're excited to have Dr. Serreze with us. He is a geographer and director of the National Snow and Ice Data Center at the University of Colorado Boulder. He studies sea ice in the Arctic and elsewhere. Dr. Serreze, thanks so much for joining us.
Oh, thanks for having me. It's a real pleasure.
Yeah, so you started working in the Arctic in the early 1980s, is that right?
Yeah, I was just gotten my bachelor's degree and thinking of going on to graduate school, and I had an opportunity to go up into the Arctic to do some measurements and hopefully get interested in doing work for grad school. And so I did, and I was just kind of a field hand at the time, but it was a lot of preparation and quite exciting. This was all well before internet or anything like that, GPS. It took us several days to get up there, up to northern Ellesmere Island. This was way up there, about 80 degrees north. And I just got out of this little ski plane and got out and just looked around, and it was like, wow, this is incredible. This is the Arctic, this pristine, unspoiled beauty. It's just, I got hooked right then.
And so what was it like then? What did it look like on the ground? Before we even start talking about data and satellite images, what changes have you seen on the ground over that time span of working there?
Well, things really have changed. You see it in a lot of different ways. In terms of on land, for example, where you're losing the snow earlier in the spring. Of course, the Arctic's very white, the land's in the ocean as well, both. But you're losing the snow over land much earlier than you do. Where we've really seen big changes in terms of the ice cover, that's the floating ice cover of the Arctic Ocean, where we've had reductions in that ice in all months, but especially at the end of summer. Over land, we're also seeing things like changes in vegetation. You're seeing areas of formerly treeless, windswept tundra being taken over by shrubs. So there's just a lot of changes going on, and they're all really consistent with a warming climate.
To most people, the Arctic seems like it's awfully far away. How does it affect people who are never going to go anywhere near the Arctic?
Well, it's going to affect people in a lot of different ways. Now, certainly from the climate point of view, it's important to recognize how significant the Arctic is, because the Arctic is basically kind of the refrigerator of the Northern Hemisphere, kind of the heat sink. You've got a big gradient between the lower latitudes and the higher latitudes of temperature, and that's what drives our basic atmospheric circulation. The atmosphere is trying to transport heat from the lower latitudes to the higher latitudes, but by warming up the Arctic strongly, the question is, might we change that? Might we actually change patterns of atmospheric circulation, and that would go along with changing precipitation? It's a big controversial issue, but it's one of them. Another one, a real big one, which is kind of outside of the direct climate realm, is changing geopolitics of the region. The Arctic's now becoming more accessible. There's a lot of oil and gas in the Arctic, and of course we saw Royal Dutch Shell pulled out of their exploratory operations in summer, but they'll be back if prices go up. The Arctic's becoming open to shipping through the Northwest Passage or along the northern sea route. So there's a lot of things going on in that side as well. So the Arctic is, as we lose the ice cover in the Arctic, it becomes more accessible and more strategically and economically important as well. Those are just a couple of examples of why people living in the lower 48 or elsewhere should be concerned about what's happening up in the farm.
So give us an overview of how do you measure Arctic sea ice, and what are those measurements telling you?
Well, sea ice is something we can measure from satellite. We have many different satellites that are orbiting polar orbits from which we can get information on what's happening in the sea ice cover. One of the most important ones is from what we call passive microwave. That is basically radiation in the microwave wavelength emitted from the surface. And the thing is that sea ice emits microwaves very different than, say, over land or over open ocean. And you can use that instrument to be able to identify where the sea ice is. And the other thing about the passive microwave imagery is that we can see sea ice, or basically sense what sea ice is doing, independent of cloud cover, independent of polar darkness. So it provides that all-weather capability. So that's one of our most important assets we have. And that record we've got from the satellite goes back to 1979. We've got other forms of extended back, which is fairly good accuracy, and other forms have been back further. But what all these things are really showing that since the onset of the satellite, a lot of sea ice. If we look at the September sea ice now, compared to say we're in lost 30 or 40.
So I think, could you try getting closer to your microphone? Your sound is going in and out right now.
Okay.
So let's see whether we can, and could you summarize a little bit of that? Because some of that was really important for people to hear, okay. And I'm not sure people would have caught it everything, but.
Does that sound a little better now?
Yeah, that's better.
Yeah, okay. Yeah. Point is we have very good records of the sea ice cover and how much sea ice we have from satellite data. And that extends, our primary record extends from 1979 onward. But we have other sources of information that we can take it back to the early 1950s, other sources we can take it back even further. And what these collected data are showing us is that we are losing sea ice rather rapidly over the past 30 or 40 years. If we look at September, compared to where we were in the early 1980s, we've probably lost about 30 or 40% of it by now. So it's really going fast.
So why focus so much on the Arctic sea ice versus ice in other places or at the South Pole?
Well, of course, we look at the sea ice in the Antarctic as well, both of our polar regions. And the Arctic is quite different. The Antarctic sea ice are quite variable, and in some areas, now there's very good reason for this, because the geography of the Arctic is so different from the Antarctic. The Arctic is an ocean surrounded by land. The Antarctic is a small ice sheet surrounded by ocean. There's no reason to heating they aren't actually.
So you're coming in and out again for some reason.
Yeah. Well, I'm hearing a lot of static as well. Okay. So there's something else going on here. Am I okay right now?
Yeah, I can hear you right now. Yeah. It was just for that answer for that question.
Yeah. I don't know what was going on there. I was hearing a lot of static.
Huh. Okay. So just to summarize, the Antarctic is variable and very different than the Arctic.
That's right. You're right. The sea ice covers in the two hemispheres are behaving very, very differently. The Arctic, we're really losing the ice fast. The Antarctic, actually quite variable and increasing in some areas. But the physical geography of these two areas is so different that really helps us to understand why they're behaving so differently.
So you mentioned that that the Arctic sea ice is going very quickly, but predicting exactly when, forecasting when the sea ice might be gone. is difficult. So, or when the ocean will be ice-free. Its predictions have ranged from 10 years to 85 years from now. And you've said you think it could be by 2030. So why is forecasting the sea ice extent and decline so difficult?
Well, it's a number of reasons. First of all, there's a lot of natural variability in the system. Just like here in Colorado, we might have a few winters where it's cold and snowy, followed by a few where it's warm and not as much snow. The Arctic is also prone to this sort of natural variation in climate. And so it makes predicting the future difficult because we have this variability in the system. So the pattern we expect is that overall we'll be losing sea ice. However, within that, there'll be a lot of ups and downs in terms of rises and falls in the sea ice cover. And these dips could last even a decade or even longer. So we'll have periods of rapid loss, maybe not so rapid loss, even periods where sea ice is increasing. And so this alone makes it difficult to know when we'll really lose the sea ice cover. Say we'll have a seasonally ice-free Arctic Ocean. There's also still a lot of uncertainty in our models themselves. There are certain processes involving sea ice cover, which we don't model as well as we think we should. So that introduces uncertainty as well. But one of the other very important issues here is that it depends on us because it really depends on what the future rates of greenhouse gas emissions are going to be. And we don't know that. So it is up to us. So when someone asks you, for example, how warm is it going to be in the Arctic 50 years from now, it's actually not a very well phrased question. A better phrased question would be, if we assume a certain growth rate of greenhouse gases, what might be the warming that we get? And so the same thing holds for sea ice. In large part, the future is up to us.
So what would a seasonally ice-free ocean look like for the rest of the world? What, you know, you mentioned that the sea ice has been declining at a rate of about 13.4% per decade. What would that be like, and how would it affect people's lives?
Yeah, well, when we say seasonally ice-free, we have to be careful in how we define that because even for a long time, there'll be a little bit of ice around. Usually when people talk about seasonally ice-free, the thinking is something like less than 1 million square kilometers. And what that means really is that if you look at it from satellite, it looks like a blue ocean. And it'll be pretty much wide open. You can sail right across it. Now, the thing is, we have to remember when we talk about ice-free, we're talking about ice-free. Because even in a warmer world, it's cold and dark in the Arctic, and there will be ice. It's just that ice is not a seasonal thing. It's warm in autumn and winter, will melt through spring and summer. End of summer, we'll have a blue ocean.
So in 2012, the extent of the Arctic sea ice hit the lowest point it's been since it started being monitored by satellite in the 1970s. What was your reaction to that, and what does it mean for us?
Well, of how low we got, the actual number we ended up with, that was surprising that it could get that low that quickly. On the other hand, part of the overall that was occurring. This different they're really high or really low. One thing that's very important was the summer weather pattern. And some years the summer weather pattern is set up nice, and so you have a lot of light. Others set up as well. So you have the next here. 2012 was a warm summer, so that really helped you. A lot of static.
Yeah, it was harder to hear you on that one, but you said that 2012 was a particularly warm summer.
Yeah, it was a particularly warm summer, as was 2007, which was the record year before that. The last couple of years, not so warm. So after 2012, we recovered. recovered a bit in 2013, but then we dropped a bit in 2014, dropped a bit in 2015. And what will happen next year? Well, we know it will be a low year, but where it's going to sit in the record books, can't say.
So how much sea ice are we talking about? You know, you guys have talked about millions of square kilometers of area, but can you put that into perspective for people who might not think in millions of square kilometers? How much ice are we talking about?
Well, it's always, if we can compare it to, say, the contiguous United States, right? It used to be, basically, like if we thought about the early 1980s, how much ice would we have in September? And it turns out, if you run the numbers, it came out pretty close to the area of the contiguous United States, the lower 48, minus Senator McCain's home state of Arizona. Just turned out the numbers worked out that way. If you look at where we were in 2012, you could think of, in terms of the sea ice loss, as throwing out all of the states east of the Mississippi, as well as North Dakota, South Dakota, Iowa, Nebraska. That's how much we had lost. And so that, I think, really tells you this is a lot of real estate that we're talking about. So 2013, we recovered some. 2014, down a bit. So maybe we could, you know, for those years, we could pick back up Iowa, say Nebraska. Okay, but we are losing it quickly, and I think this comparison really helps people to understand just how much of a loss there is. It's a lot of real estate.
And so the ice does fluctuate over time. So some years you may lose a lot, and others you may gain some back. What does that mean for the age of the ice?
Well, what we're seeing is that one of the things we can get from satellite pretty easily is the extent of ice. That is how many square kilometers, how many square miles of ice there is. What we'd really like to get very good records of is the thickness of the ice, because really that's the overall, that's the better sort of more complete estimate, ice volume or ice thickness. And that's harder to get. But the one thing we can get from satellite data is, interestingly, is the age of the ice. And it used to be that we would have ice in the Arctic Ocean that might have been floating around or drifting around for 10 or more years. And now we don't have that anymore. We're losing all that old ice. The thing is, the old ice is the thick ice. Old ice is the real resilient ice. The ice that used to be able to take a punch. When a warm summer would come through, you'd have this old thick ice. It could survive. It could take that punch. Now you don't have that anymore. So when you have a particularly warm summer, sea ice responds much more readily now. It's much more sensitive. And why we have this ice of different ages is very interesting in itself. If you think about how this works in the Arctic, we have some ice in the Arctic that will form through an autumn and winter season. And now summer comes along, some of that will just melt away, but some of it won't. Some of it will survive. If it survives the summer, then it becomes what we call second-year ice. In the next winter, that second-year ice can get thicker because it will grow from the bottom. The next year comes around, some of that second-year ice melts away, but some survive. And so if it survives, it becomes third-year ice, and so on. It becomes thicker and thicker. And so you have this process always ongoing. And so if you look at the Arctic, at least in the past, you would have ice that was 1 year old, 2 years old, 3 years old, some of it 10 or 12 years old. But now, no more. Finding anything, say, 5 years older, 5 years or older is pretty tough now.
So we've got a question from the audience. Oops, I think I selected the wrong one. Given the variance in models, greenhouse gas emissions, and scalloping of the ice shelves, how predictive can we be with regard to loss of sea ice versus sea level rise?
Oh, that's a tough question. Now, in terms of sea ice, as I just already mentioned, there's a very wide range in terms of predictions of when we might go essentially ice-free in summer. Certainly within this century, but apart from that, it's hard to say because, as I said, one of is the big natural variability in the system, which I think the viewer has already mentioned. Our models are not as good as they need to be, and also the unknowns in terms of what the greenhouse gas emissions are going to be. Now, in terms of sea level, we have to remember that sea level is actually a different problem because if you melt sea ice cover, that actually has no effect on sea level because this ice is already floating. It is basically Archimedes' principle at work. When we're talking about a sea level rise, we're talking about two things. We're talking about the effects of a warming ocean and the effects of taking ice that was on land and dumping it into the ocean. By the warming ocean, the issue there is what we call thermal expansion, in that the density of water is actually not constant. It depends on temperature. And so if we warm the ocean waters, which we are, the ocean occupies a slightly larger volume. That's part of your sea level rise. The other part, of course, is meltdown of ice sheets and glaciers, and that is something that is happening. Now, we've pinned down the overall rate of sea level rise today fairly good. It's around 3 millimeters per year. Now, that doesn't sound like much, but it's year after year after year after year. And so we can actually measure that fairly well. Where some of the unknowns are still is in what's the relative contributions of things like the Greenland and Antarctic ice sheet versus the smaller glaciers around the world. So we're still not through with doing the final budget here, doing all the accounting. But at least the overall sea level rise, we kind of have a good handle on what that number is, and it looks like that number is going to increase in the future. But like any of these issues of climate change and where we're going to go, there are unknowns out there. There are uncertainties out there. There are wild cards out there.
So why is warming so much stronger in the Arctic than it is in other places throughout the world? Why are we seeing, if you look at just where warming is happening, it's really concentrated around the Arctic?
Well, it's interesting. There was a guy back in 1896, a guy named Svante Arrhenius, who asked the same question. And he figured it out, basically, all the way back then. It has to do with feedbacks. The issue here, what Svante Arrhenius was saying in 1896, is that if we put carbon dioxide in the atmosphere, more than fossil fuel burning, what he called carbonic acid back then, the Earth would warm. He understood this all the way back then. But he also stated that the warming would be greatest in the polar region. And that's because of feedback. The basic idea that what was he was getting at, even back then, is if we look at the Arctic, it's white. It's largely covered with snow and ice. But that snow and ice reflects most of the sun's energy right back into space. But if we warm the climate up a bit, what happens is some of that snow and ice melts. It exposes darker surfaces underneath, darker tundra surfaces, ocean, dark ocean, and that more readily absorbs the sun's energy. So it absorbs more energy, it heats up more, so it gets even warmer. So that's what that's in a nutshell why one of the biggest reasons why this would occur. Now there's others as well in terms of the very strong stability in the Arctic of the atmosphere that traps near the surface. Changes in atmospheric circulation that we've observed appear to play a role. Changes in cloud cover appear to play a role. But these sort of feedbacks I talk about, especially this one involving snow and ice, that's really the biggie out there. And Svante Arrhenius predicted it back in 1896. Here we are. That's exactly what is happening.
So that kind of leads me into another question I had for you, where could you describe some of these different feedbacks in a little bit more detail? The feedbacks that exacerbate the global warming that we're seeing, especially in the Arctic.
Yeah. Well, I mentioned, of course, this one about snow and ice, and that's called albedo feedback because albedo is just a fancy word for the reflectivity of the surface, and so that's where it gets its name. Now, the other one that's out there, the biggie, that, of course, operates in the Arctic, but elsewhere across the globe, is a water vapor feedback. That water vapor is actually the most abundant greenhouse gas in the atmosphere. It's a very important part of what we call our natural greenhouse effect. Without it, we'd be in a whole lot of trouble. It's just that too much is not a good thing. But the issue here is that if you warm up the climate a little bit, the atmosphere can hold more water vapor, and it will hold more water vapor. But water vapor, as I just said, is a greenhouse gas itself, and so that causes even more warming. So those are two of the real biggies: the albedo feedback, the water vapor feedback. former operates more in the polar region, but the latter operates everywhere. Now, another important one in the Arctic that people are looking at very, very carefully is the carbon cycle feedback. The issue is this, is that if you look across the Arctic landscape, there is a whole lot of carbon stored in the soils of the Arctic. This is old frozen peatlands, things like that. How much is in there? More than is in the atmosphere today. The concern is if you start to thaw and warm the permafrost in the Arctic, that means the little microbes in the soil become active. Respiration ensues, and this will cause a release of carbon back to the atmosphere, either as carbon dioxide or as methane, depending on the situation, and that will then increase the load of atmospheric greenhouse gases. And so people are really looking at this in the Arctic. There are big questions out there, of course. When might it begin? If it kicks in, how important will it be? Will it be something like, just 5 or 10 parts per million of carbon dioxide in the atmosphere, or will it be something much bigger? And so that's another example of these wild cards out there, the things, sort of the known unknowns out there that we've got a lot of scientists looking at, and we've got a lot of questions. Those are sort of three of the big feedbacks, I would say.
So can this decline in Arctic sea ice be stopped? And can we prevent us from getting to the seasonally ice-free ocean?
Oh, sure, we could stop it if we really wanted to. If we look at what our climate model projections are saying, what we look at is different scenarios of greenhouse gas emissions, and we can see how the sea ice would respond to those. There's one we call these representative concentration pathways. RCP is the fancy word, but the real aggressive one is kind of the burn baby burn scenario, and on that one, the Arctic sea ice is gone well within a century. But a more modest emissions scenario where greenhouse gases rise, but then level off because we take action. By the middle of the century, we could preserve the sea ice. It would be less than today, okay? But there would be still enough there, and it could recover. The thing is, if we could get the extra CO2 out of the atmosphere, which is a pretty hard thing to do, the sea ice would actually recover fairly quickly. As far as we could tell, it would recover fairly quickly. The question, of course, out there is, are we going to do this? And of course, there's a lot of conversation going on right now in France addressing this very issue.
So with the Paris climate talks happening as we speak, what do you hope to see come out of the UN Paris climate talks?
Well, I would hope that agreements could be made to reduce greenhouse gas emissions. Realistically, this is going to be very, very difficult because it's a worldwide problem. Who are we to tell China, to stop emitting greenhouse gases? When they're just trying to get a better life for themselves, just like we are. But it would take a global commitment. The thing is, though, we have to be realistic about this. And so people ask me, what do we need to do about global warming? And I said, the first thing you need to do is adapt. Because the world is warming, it's going to continue to warm. And so we are already in a warmer world, and it's going to get warmer, no matter what we do. Because there's still heat in the pipeline that we haven't caught up with yet. The real challenge, I think, what we can sensibly do and realistically do is get a handle on this problem before it gets out of hand. That's really where I think there's still possibility here, but it's a tough nut to crack. It's going to be a worldwide commitment to this, and that's a tough road.
So climate change communication is now, it's kind of like a textbook case of how scientific consensus can be miscommunicated or fail to be communicated to a large group of citizens. Have you changed how you talk about climate change over the last 20 years to try to get the message to new people who might not necessarily be receptive?
Oh, certainly I have, and many scientists have. There was a time when most scientists were just happy sitting in their their ivory towers, as they say, doing their science and being satisfied with that. But the role of the scientist has changed very much. And rightfully so, because it is really, I think, the responsibility of the science community to make their results relevant, to allow people to understand what is happening and the importance of what they do. This is still very tough for scientists because most of them are not trained in this. But we are seeing a change, certainly in the younger generation of scientists coming up. They understand implicitly that this is part of the responsibility of being a scientist now. For myself, it's been a long road. I mean, I was just like many others doing my work back, when the Arctic was just a cold place, and now we're in a situation where the Arctic is seeing this big change, and we're suddenly called upon to try and communicate what's going on and let the public understand where we may be headed. And it's been a very tough education process. And it's not something you really can learn from a book. It's not something you can go to a seminar and learn from that. You have to just do it. That's the only way you can really learn it, is by doing it and by making mistakes. And I made my share of mistakes, but I continue to learn every day, and I think venues such as this is exactly what we need more of.
And so do you have any particular things that have worked for you? Have you spoken to students or spoken in the public where you feel like maybe you've at least had somebody recognize climate change as more of a problem than they did before?
Sure. There's many different ways. And I think one of them is to make the science accessible. Scientists very typically could just fall into their own scientific jargon, and someone hears them and say, what the heck are they talking about, right? So there's what you really need to try and do is make the science accessible, but also keep the science there, keep the science rigor there. And some people will say, well, you can't do that. Well, you can't. You can if you try. You can use analogies. You can use different phrasing to get the idea across without really losing the rigor. And also, I think, is that you've got to stay objective, and you've got to avoid getting into advocacy. I think that's a danger that I see a lot of people getting into. A big problem that I see personally in terms of the climate change issue is that the shrill arguments on the left that the sky is falling and we're all doomed are as equally unhelpful as the shrill arguments on the right that, this is all a conspiracy or nonsense and let's not worry about it. The truth lies, of course, as things do, somewhere in the middle. We've got a problem, a looming problem. We need to deal with it. This is what we think is going to happen. We have to have that sort of rational discussion and not get too emotional about these things, because you can't make progress by looking at things from these extremes. That's not going to get you anywhere. We just need to have a reasoned, rational discussion about these things. Hopefully, I think that's very important in trying to move forward.
And so what are you seeing now? What are you expecting this winter to be like, next summer to be like? Do you have any, at least obviously predicting long term is difficult, but in the short term, what are you thinking?
Let's say look at the sea ice cover for this September. What is it going to look like this September? Well, I can tell you with near certainty that it's going to be well below average. In other words, if we looked at an average sea ice extent for September based on some period, say 1979 through 2000, something like that, and we compared the upcoming September sea ice with that average, we'll be below that. Absolutely. I don't think we can. I'd be very, very surprised if we could get above that, because there's just too much warmth in the system now. We can't go to a situation right now like we saw back in 1980. That would be pretty hard to do. So we know, I can tell you right now, I'd be extremely surprised if sea ice didn't end up well below average. Okay? But where will it set in the record books? We haven't a clue. We don't. And that's because of the variability of the system. We can say certain things, say this spring, about if we wait until the spring, we could tell you more, because we could give you an estimate of what's the distribution of the thick ice and the thin ice from this ice age thing I talked about, right? Mm-hmm. And if we start the season with a lot of this thinner ice, well, that'll tell us quite a bit about the summer because it doesn't take as much energy to melt out thin ice than it does the thick ice. It makes sense. But so much of what happens depends on the summer weather patterns. So next summer, do we have a warm weather pattern that overall sets up that gets rid of a lot of ice, or do we have a cool summer weather pattern that sets up which preserves some ice? We don't know. Our capabilities are not that mature to be able to say that, and that's just the reality of where we are and some of the limitations of trying to make predictions.
So here's a question from the audience. Are gains made so far enough to offset the Arctic melt?
I'm assuming the gains made in carbon, in greenhouse gas emissions.
I think that's what they're saying.
I would say no right now. I would say if current trends continue, we are absolutely destined for an ice-free Arctic Ocean sometime in this century. When, of course, is a question. So no, I don't think the gains that we've made are nearly enough. And again, I think what we really got to be focusing on is just slowing down the greenhouse gas emission enough, okay, so that we can keep this from getting out of hand, start to bring on better technologies. Conservation is a huge thing. I mean, if you ask, what can we do today to put a huge dent in carbon emissions? Conservation, absolutely. That is the soft underbelly that we've got right now. We are so wasteful in our energy. That's the soft underbelly that I think we really be putting a lot of focus on.
So we have another question from the audience. This one, I think, is maybe you might have to go back and review some of the information about how ice melt affects sea level rise or doesn't. This question is, you mentioned that the Arctic is losing ice while the Antarctic is gaining in a few spots. Are the gains enough to offset the Arctic melt?
No. No, certainly not right now. But we have had periods where if you looked at total sea ice cover for the globe, okay, that you would have a balance, somewhat of a balance occurring because we've been losing it in the Arctic and we've been gaining it a bit in the Arctic, certainly in some areas. And so there is certainly an offset that goes on there. But really the question is, we would say, well, one might say, you've got this balance, so why worry? Okay? We're all fine. And the answer is no, that's really not the way to look at it, because it's a matter of understanding what the processes are. If you look at the Antarctic, it is warming, and the thing is, the Antarctic ice sheet is contributing to sea level rise. The Antarctic ice sheet is losing mass. And of course, the Arctic is warming up. So certainly in terms of the sea ice, there is somewhat of a balance that occurs, because you lose it in the Arctic, and we are gaining it, at least in parts of the Arctic. But I don't think we should be thinking of that as saying, oh, everything's okay because of that.
So can you put the Arctic sea ice decline in a historical or prehistorical and ancient timeline, geologic timeline context? So we have had an ice-free Arctic before. What was it like back then? What does that mean for now? How does that compare to the greenhouse gases that were in the atmosphere at that time, et cetera?
Yeah, well, people ask when might we have last seen an ice-free Arctic Ocean? And I'm saying seasonally ice-free in summer. And actually, we don't have a very good handle on that, because these sort of proxy records that we call paleoclimate records for something like that are hard to come by. Probably we were close to it at least, or maybe we had an ice-free Arctic at times during the last interglacial that we had. That was called the Eemian interglacial. And that was about 125,000 years ago. Now, the reason why it was so warm in the Arctic at the time was what we call Milankovitch forcings. Okay, so what this is that if you look at the relationship between the Earth's orbit and the Sun, that changes. We think about the tilt of the Earth. We have a 23.5 degree tilt. That gives us our seasons. At times it's been bigger, at times it's been smaller. And so that means our seasons have been stronger at times and weaker at times. Warmer summers, colder winters. Also, our eccentricity of our orbit has changed. So right now, we're closest to the sun, actually in winter, interestingly, and somewhat farthest in the summer. And there's several of these things that occur. They call these Milankovitch effects. And it turns out that when you want an interglacial, like we had 125,000 years ago, you get a setup of these orbital configurations just right, that it can do a very, very warm northern hemisphere summer. And that was the case back 125,000 years ago. Now, the thing is, we're in an interglacial now, right? Kind of like the Indian. And are we close to the overall warmth of the Indian? Okay, we're close right now, and we're getting closer. Right? Now, there were probably times back 125,000 years ago we probably were ice-free. Now, other people have said that maybe it was 1,000 years ago as well, because what we were in that situation was what we call a Holocene thermal maximum, is what it was calling. And this was when we came out of the last ice age. And again, we had these orbital forcings set up in just the right way to give us a very, very warm Arctic. It was possible that we saw it back then. But again, we don't really have the information we'd like to be able to say definitively yes or no. But certainly there were times in the past. But what we're seeing now, of course, is something in terms of when we're talking about these Milankovitch effects, we're talking about changes occurring over thousands, tens of thousands of years. Here, today, we're talking about something in less than a century. So it's the rapidity of change that's really very different in this case.
So I'm going to jump back. We have a question that relates to when we were talking about the age of the ice, and this question is how do you measure the age of the ice from the satellite?
Yeah, well, it's from a feature tracking approach, actually, in that if we have sequential satellite images we can use, you can actually feature track the ice. In other words, you look at the imagery, you see a certain feature in the ice, and you look at an image from the next day, you can see how that particular feature has moved. And so you can actually track it in this way, basically through a feature tracking approach. So it works surprisingly well. You might not think it does, but it actually does, and we can get very nice maps now of the overall age of the ice cover from this approach. But it really is just a statistical feature tracking approach.
And so how do you know that feature, you basically know how buried it is under the ice and then how old it is when it first showed up in the...
No, it's just a feature. Like if you look down from if you're up in an airplane looking down at the surface, you can see features, right? You can see houses, you can see lakes, you can see things like this. Well, if you're up in orbit looking down at the sea ice cover, different parts of the sea ice cover actually appear different. They could have a different roughness texture that you see, a different brightness that you see, and that's the information that you use. Right? So think of a ship in the ocean. Okay? If you were looking at a ship in the ocean from a satellite, that would be a feature. Right? If you look at it the next day, now it's out here. You can track that feature. Right? You can see how it moved from here to here, and from that you can draw a vector from one location to the other location. The same basic idea that you use is enough features or sort of heterogeneity in the ice that you can see these features, that you can use those to track. That's how it works.
Okay, let me make sure I'm not missing any questions before I ask some more. So explain what the Northeast and Northwest passages are. You mentioned them early on as being part of the changing geopolitics in the Arctic. Why those are politically relevant, and what your research says about how sea ice decline will affect them.
Yeah. Well, okay. So if you, let's say you have a boatload of Toyota Priuses, right, that you've gotten from Yokohama, right, and you want to get them to New York. Well, the traditional route would be either you go through the Panama Canal if you've got a small enough ship, what we call a Panamax ship, or if it's too big, you have to go around Cape Horn and around the other way. Well, of course, the dream is that you don't have to do that. You can go right across the Arctic Ocean and take your boatload of Toyota Priuses right across and bring them down to New York or wherever you're going. And where you would do that is through one or two routes, either what we call the Northwest Passage or what we call the Northern Sea Route. Now, the Northwest Passage is a passage that goes through the complex channels of the Canadian Arctic archipelago. So if you look at the United States and look to the north into Canada, you'll see all those islands up there, the far north. That's the Canadian Arctic archipelago, and there's numerous channels through there. And what we're seeing is now that those channels have becoming relatively ice-free in recent years, and so those channels are opening up on a seasonal basis. That's the Northwest Passage. The Northern Sea Route is on the other side. That's along the Russian side. Now, the Northern Sea Route is becoming probably even more open than the Northwest Passage. That may be the more viable route. Those are the two passages. Now, the thing is, these, in terms of how much these could be used or how valuable they could be used, number one, you have to remember that these are going to just be seasonal passages, because even in a warmer world, it gets cold and dark in the Arctic and sea ice will form. So there'll be seasonal passages. So that's one thing. And how economically viable will they be in comparison with other routes? Okay, for example, as we know, the new locks in the Panama Canal are almost complete, or I keep hearing they are complete or almost complete, but it's just about there. But they'll be able to deal with a much higher capacity. So when that occurs, well, does the Arctic, for example, in the Northwest Passage or the Northern Sea Route become less attractive? Right? We'll see. These are among the kind of unknowns we have out there. Now, some people will say, well, we talk about the Northwest Passage was open last year, which it was, at least the southern route, we call the Evanston route. We've had people say, well, no, people have been using the Northwest Passage for years. Evanston did it back in the turn of the century, 1901, 1902, right? True, he did it, but it took him 2.5 years to do it because it was choked with ice. Nowadays, there are some years now where you could literally take a sailboat through the Northwest Passage and come out on the Atlantic side, or go to the Pacific, depending on which direction you're going.
Great. Okay, we have a couple more questions. We've had this question a couple of times in a couple of different ways, so I think the audience wants it answered. But they're asking about how much methane is trapped in the frozen tundra and whether we can predict or model its release, which seems, since it hasn't happened, it seems like that might be difficult to do.
Right. So the issue here, and I mentioned it before, is that the concern about this carbon cycle feedback. And the idea that most scientists have been focusing on is on land. That there's all this carbon locked up on the land. And as the permafrost thaws, the microbes in the become active, respiration ensues, carbon is released to the atmosphere. And that would either be as carbon dioxide or as methane, depending on the process. Methane would be an anaerobic process of oxygen, and carbon dioxide the other way. And again, there's concern about that, but a lot of unknowns. Now, there's also been a lot of discussion about a massive methane release from the seabed of the Arctic on the continental shelf.
You said a
massive release of methane.
Okay.
Of methane. I was getting a little more of that static again here. I don't know where it's coming from. It looks to be clearer now. But a massive release of methane from the seabed of the Arctic. And the issue here is that underneath these continental shelves, there is a lot of methane trapped in what's known as a clathrate. That is, it's in an icy form. And it turns out, under certain combinations of pressure and temperature, you can form these so-called clathrates, ice that burns, literally. You have this ice that would burn. Well, their concern is that, well, if we warm up the Arctic Ocean, maybe we could have a massive release of this methane. The clathrates would melt and we have this massive release. Now, there have been observations made of bubbling methane from the ocean bed rising to the surface. And that's got a lot of people thinking about, could we have such a thing, an event occur? One of the big problems is we have no context for it. We've observed these bubbles rising and things like that, but we don't really know what things looked like 30 years ago, 50 years ago. We don't have the context here to say much. Furthermore, from my understanding of the science on it, to get such a massive release of methane from the seabed would be actually very, very difficult to do. Very hard thing to do to get a big, massive release, although people are talking about it, and rightfully so. I think most people have viewed this as a low probability event. What would be happening over land is the higher probability event. So yes, the idea of these massive methane releases is there, but I would say we have bigger fish to fry, really.
So explain also the potential for offshore drilling in portions of the Arctic, especially off of Alaska's coast. That area has been really contentious of late. Tell us about that issue and how your research relates to it.
Yeah, well, that issue, of course, is that there is a lot of oil and natural gas on the Arctic seafloor, especially along the continental shelf. Now, some of that we're well aware of course. For example, there's been drilling at Prudhoe Bay for a long time, but they've also been drilling in the very shallow parts of the Beaufort Sea on like man-made islands and such. But a number of leases were opened a while ago in the Chukchi Sea. So that's kind of the north and west, okay, still north of Alaska, but kind of west of Prudhoe Bay. And so there's been a lot of interest in that. And Royal Dutch Shell, of course, went up there this summer with their big rig. And they did drilling, and they came back, and they were disappointed with their results. And they said, well, we're not going to come back, at least for a while. Right now, oil's less than $40 a barrel. Last I checked, it was right around 40. Well, when it gets to $100 a barrel again, it might be back. Now, there's, of course, a lot of other reserves in the Russian waters, right? Vladimir Putin owns that stuff, right? Or he says he does. So that's another issue. But in terms of us, the U.S., the interest has really been on like the Beaufort Sea and the Chukchi Sea. Now, how our work relates to this here at SIDC is that a big issue here is sea ice predictability again. So what anyone operating up there would like to know when, say, in the Chukchi Sea, is it going to become open? In other words, when it will open up in spring with no ice, and when is the sea ice going to come back in autumn? I'd like to know, when I could get my rig up there, how long I could keep it there, and when I've got to get it out. And so what you're seeing because of that is a lot of renewed work on the sea ice predictability issue, but on the regional sense. When we think about climate issues, what we're really interested in is when will the Arctic Ocean go ice-free, something like that. If you're working for Royal Dutch Shell, you really want to know what's it going to be like in the Chukchi Sea, right? This small region. That's the regional focus that I'm interested in. And so you're seeing a lot of renewed work and interest in this sort of thing. Very, very much applied science. And of course, we're well aware of the irony here, right? We're losing the sea ice because of climate warming, and now we're, of course, making the oil there and natural gas more accessible. But this is the crazy world we live in.
So we've got just a couple more minutes to discuss. I wonder whether you have any closing remarks or things you want to make sure that people understand.
Yeah, well, I think that what I try to emphasize is that climate warming is not something out there 30 or 40 years ago, out there in the future. It's here. It's already happening, and the Arctic is leading the way. We had long predicted that the Arctic is going to warm the most, and that's exactly what's happening. And so it's a nice, wonderful case of our predictions becoming true. But in terms of the issue of what we need to do and how we should deal with it, again, I emphasize that we have to be pragmatic. We built a huge society, a global society around fossil fuels. The incredible amount of energy in a lump of coal or in a gallon of gasoline. We built a society around this. Everything that we touch and use is built in some ways on mining or petroleum, one way or the other. And no one wants to go back to a Stone Age. Okay? So we built this whole society around this. What we didn't really realize was that it's a trap. And so we've got to be pragmatic about it. Here we are today. Let's come forth with practical solutions. We are going headed for a warmer world, but now let's get together and deal with this before it gets out of hand. And that would be that's my view on this.
And by dealing with it, do you think renewable energy is one of the ways that ways forward?
Oh, sure. Renewable energy is absolutely one of the ways forward. Conservation is huge. Okay? Now, I'm on record, very controversial, I'll say it again. I'm pro-nuclear. Okay? Why? Because certainly there are issues with that, of the dealing with the nuclear waste and the cost of building these things. I'm well aware of that. Okay? But it's an issue of choosing your own poison. Okay? Nothing comes for free. There are no easy solutions to this. There are only intelligent choices.
So before we close, I just want to mention that we have one more Hangout. Well, we'll have more in the new year, but one more for 2015. That's on December 15th. It's going to be on nanotechnology and DNA with Bryant Nelson of NIST. And then I want to thank Dr. Serreze for coming and joining us. I'm not sure whether to tell you to stay warm or stay cold up there. But
well, we'll do it one way or the other.
Well, thank you so much for explaining your work to us, and I wish you the best of luck with it.
Okay, thanks, and it was a pleasure being here.
Bye-bye.